What's up, guys? We're doing lesson 84. We're going to multiply radicals, and we're going to talk about function machines. Stay tuned.
Flack math! Give me some math and I'll give you some flack. Flack math!
All right, lesson 84. Here we go. Okay, we've already talked a little bit about multiplying radicals. So here's the rule. Whenever you have a radical times a radical, you can just multiply them together to make one big chubby radical. Square root of 2 times the square root of 25 is the square root of 50. Because 2 times 25 is 50, so the square root of 2 times the square root of 25 is square root of 50. All right, so generally, the square root of anything times the square root of anything else equals the square root of that anything times that anything else. So square root of m times the square root of n is the square root of m times n, okay? And you can go backwards. Remember, square root of mn equals the square root of m times the square root of n. So we're going to step it up a notch. It's just multiplication, right? So you can multiply anything together. So let's try an example here where we multiply radicals along with other numbers as well. So for example, if we have 4 times the square root of 3 times 3 times the square root of 2, well, this is just 4 times the square root of 3 times 3 times the square root of 2, right? Well, in multiplication, it doesn't matter what you do first. You can switch the order of everything you're multiplying so that you could just say that this is 4 times 3 times radical 3 times radical 2. Well, that's just 12 times radical 6. So when you have a number times a radical times another number times a radical, multiply the numbers outside the radical first, and then multiply the radicals together to make one big chubby radical. So let's try another one. Example 2. 4 radical 3 times 6 radical 6. Well, multiply the numbers together, 24. Multiply the radicals together, radical 18. Done? No. So there should be a little alarm going off in your head. Say something's not right here. Here's what's going on. There's a square hanging out inside of that radical. Remember, squares do not belong inside of radicals. We have to get it out of there. So how do we get it out of there? We simplify the radicals. Remember, the magic question when you're simplifying radicals is you have to ask yourself, what is the biggest perfect square that I can divide out of that radical? Okay? Well, in this case, remember perfect squares are like 1, 4, 9, 16, 25, and so on, right? So these are all the perfect squares. So what is the biggest perfect square that I can take out of there? It looks like 9. Here's what it's going to look like. 24 times, well, this is just radical 9 times radical 2, right? Since 9 times 2 is 18, square root of 9 times the square root of 2 is the square root of 18. Why did we do that? Because now we can simplify this part right here. So this is just 24 times 3 times the square root of 2. So multiply that out, 72, radical 2, boom. So after you multiply everything together, make sure your radical is simplified. If not, simplify it. Good, good? All right, example 3. Here we go. So this is just a distributive problem. No problem. Remember, distributive problem is kind of like a 2-for-1 problem. Instead of just multiplying 2 things together, you're multiplying a couple things together. 6 radical 3. So we're going to multiply the 4 radical 3 times 5 radical 2, and then we're going to multiply 4 radical 3 times 6 radical 3. So let's do that. So that's 4 radical 3, let's just write it out right here, times 5 radical 2 plus 4 radical 3 times 6 radical 3. Multiply them together. 4 times 5 is 20. Radical 3 times radical 2 is radical 6. Multiply these together. 4 times 6 is 24. Radical 3 times radical 3. Well, what happens when you multiply a radical by itself? It cancels itself out. But if you don't remember that, let's just do it the long way. Radical 3 times radical 3 is radical 9. Well, what's radical 9? That's just 3. So then you have 24 times 3. So you got 20 radical 6 plus 24 times 3. So your final answer, 20 radical 6 plus 72. Boom. All right, one more example here, and then we're going to move on to function machines. 4 radical 2 all times 3 radical 2 plus 5. All right, let's distribute. So 4 radical 2 times 3 radical 2 plus, so that was that first problem, that first rainbow, 4 radical 2 times 5. Second rainbow, here we go, 12 radical 4. Well, we know what radical 4 is, right? And then 4 radical 2 times 5. Multiply the 5 and 4 together, you get 20 radical 2. Well, the square root of 4 is 2. So 12 times 2 plus 20 radical 2. 12 times 2 is 24. 20 radical 2, you're stuck with that, so just leave that alone. There's your final answer. So moving on, we're going to talk about function machines. A few lessons back, we talked about functions, okay? So for example, if this is a function here, let's say the function is x squared plus 5. So when you plug in a number like 2, what happens to it? Well, what happens when you square 2 and add 5? Well, that would be 2 squared plus 5. That equals 4 plus 5, which is 9. Okay, well, let's plug in a 3 and see what happens. 3 squared is 9, plus 5 is 14. Okay, 4 squared is 16 plus 5, which is 21. Okay, so this is an example of a function. Remember, there are rules to functions. Do you remember the rules? First rule is every member of the domain has to correspond with only one member of the range. It can't go to multiple members of the range. And the other rule is every member of the range, the result, has to have at least one member of the domain that maps to it. Okay, so you can't have this random guy hanging out in the range set that doesn't have anybody mapping to it. So if those rules are not followed, then it's not a function. We call it a relation. So every function is a relation, but not every relation is a function. So if a relation is not a function, it's just called a relation. Okay? But a relation that is a function, if it follows those two rules, is called a function. Am I just making it more confusing? Probably. Here's an example of a function. Let's say that 4 and 2 both map to 3. Okay, that's still, the rules of the function still apply. So every member of the domain goes to only one member of the range. It doesn't go to multiple things. This is a function. Okay, but if I had it the other way around, if I had like 3 going to these two different things, like 4 and 2, this is just a relation. This is just a relation. It's not a function. So as long as you don't have something in the domain going to multiple things in the range, then usually it is a function, okay? But it has to go to something. Let's do another example. Let's say we've got a couple things here, 1, 2, and 3. And let's say that 1 and 2 both go to 4, and 3 goes to 5. Is that a function or just a relation? Well, it's a function. Because remember, the only thing you have to worry about is if something in the domain goes to multiple things in the range. 1 only goes to 4. 2 only goes to 4. 3 only goes to 5. So this is a function. Okay, so both of these are functions. So you could have like things like this. If it was like 4, or if it was like A, B, and C, and then like D, E, F, and G, let's say that A went to D, B goes to E, and C goes to both F, and it goes to G. Well, that is just a relation, so that is not a function either. This can also be demonstrated with ordered pairs. For example, here's some ordered pairs. Let's say I've got a set. 4, 8 is one ordered pair. So 4, if you put in 4, it goes to 8. Okay? 15, 6 is an ordered pair. So if you put in 15, it goes to 6. 11 goes to 7. Okay? So see how the 4 only goes to 8, 15 only goes to 6, and 11 only goes to 7. This is a function. Well, let's try something else. What if we had something like this? Here's an ordered pair. 4 goes to 3, 4 goes to 5. And 2 goes to 6. We'll see how 4 goes to both 3 and 5. So this is not a function. This is only a relation. What about something like this? What if we had these ordered pairs? Well, this is kind of a trick question. 4 only goes to 3, even though I listed that ordered pair twice. So just because you have multiple x's doesn't mean it's not a function. If those multiple x's still go to that same y every time, then it's still a function, okay? All right, so we're gonna try a couple examples. I want you to press pause and then see if you can do it. So here is some more examples. Tell me whether or not you think these are functions or just relations. Okay, so you tell me whether these are functions or they're just relations. Press pause and do it. Okay, here's what I got. Let's see if you guys got the same thing. So this is a function. Why? Because 1 only goes to 2, 2 only goes to 3, 3 only goes to 4, 4 only goes to 5. A quick way to see if an x is repeated. Okay, well, first of all, if x never repeats, then it's a function. You don't even have to look any further. Okay, so look at the second example. Yes, there is an x that repeats, and then you have to ask yourself, okay, if it repeats, does it go to different y values when it repeats? Yes, it does. Because in this example, 1 goes to 2, but in this one, it goes to 3. So this is not a function. That is a relation. So look at this though. See how these guys are repeated. The x is repeated, but it still only goes to 3. So this is a function. So this is a yes. So you can have multiple x's for the same y, but you can't have multiple y's for the same x, okay? So an x can go to 1y, or multiple x's can go to 1y, but 1x cannot go to multiple y's. This was really helpful, I know. This helps you visualize everything. You're welcome. Okay, that's it for lesson 84. We'll do lesson 85 next, because 85 comes after 84.
Black man, give me some math and I'll give you some flack. Black man.